Group 6, and this is Project 4.
So we were tasked with finding the final length and the thermal stress of two metal bars, one being iron and the other being aluminum. They're in series together and they're between two rigid walls. We're told that both are 1 meter long, so the entire setup is 2 meters long. We're also told that they begin at 20 degrees Celsius, so about room temperature, and they're heated until both are 100 degrees Celsius. So we have our two equations here that we'll be using. The thermal equation will, the thermal equation, this will solve for the change in length of the iron bars with respect to the temperature, and this constant here which for each metal is different. This is the thermal expansion constant, and its units are 1 over a Celsius, which is a little confusing, but I'll explain later. And then for the stress, we have this equation here, which uses that coefficient again, and it also uses our elastic modulus that we solved for in a previous project. So starting with the iron bar, so we can rearrange the length equation to find the final length of this iron bar. So as long as we know the change in temperature, the initial length, and the coefficient of thermal expansion. So here, as I state, the coefficient for thermal expansion is 12.2 times 10 to the negative 6th. So we can plug all the numbers in. So we have 12.2 times 10 to the negative 6. We have our 100 degrees Celsius, this is the final temperature, our original temperature, which was 20 degrees Celsius, and our initial lengths, which were 1 meter. So once we take all this through, we solve, we'll get the iron bar will be about 1.00967 meters. So it's expanded that 0.00967 meters over the course of that. So now we'll go with the aluminum bar. Same thing, same equation. We swapped it, or sorry, we didn't swap it, but we rearranged it, so we're solving for the final length. And so here our thermal expansion coefficient is 23.6 times 10 to the negative 6th. And same thing as the iron, we'll just put it into this equation. It's pretty much the same exact equation other than that number. Same temperature, same length, and this came to 1.00188 meters. So it expanded farther than the iron bar. So now for the stress, we'll use our stress equation here, and we're going to use the elastic modulus of iron here. So 210 times 10 to the third megapascals. So we have our equation here, we'll put everything in. So we have our elastic modulus, we have our thermal expansion coefficient here, and then we have our change in temperature. This is also negative because in this setup, the stress is going to be negative because it's in compression and not in tension. So once we take all this through, we have negative 2.0496 times 10 to the negative 4th megapascals. And for the aluminum, doing the exact same thing, except we're changing out the elastic modulus for 69 times 10 to the third megapascals. And we have our thermal expansion coefficient from our previous slide here for aluminum. Same thing as the iron, work all this through, and we'll get negative 1.30272 times 10 to the negative 4th megapascals. Then this is the stress on the aluminum portion of this bar. And so now for the totals. So we could take our total lengths here, and we were supposed to add them, but I clearly put minus. So anyway, so we would add those two and we get 2.002864 meters. So the entire setup expanded this 0.002864 meters. Even though it's in compression, it still has expanded that far. In the final stress, we'll add them both. They're both negative numbers, so we're going to get a bigger negative number. So that comes to be negative 3.335232 times 10 to the negative fourth megapascals. And like I say here, this stress is negative because the entire setup is in compression and not tension.
And so this is like a physical evidence considering for part 2. So our initial experiment is we have 200 atoms confined into the left side of the screen, and it's at 300 degrees Kelvin. So this is just figuring out what the ratio is for how temperature and the amount of atoms for concentration can affect how many atoms are going to move over this arbitrary line. So before we start the experiment, we have this line set up so that the atoms are all bouncing around in here and they can't get to this other side. And then we measure from every 0.5 picoseconds all the way up to 30 seconds. After we take away this line, all of these atoms, how many of them are going to move over here over time? And so as you can see, if we show you the graph of how this actually represents, so over the course of the time over here, the number of atoms shows almost like a pretty linear straight line. And then there's obviously some instances where it slows down and it stays the number of atoms that don't cross over the line because they're bouncing around. Some of them are staying here, some of them are staying there. And then there's even some cases like over here where you can see it's actually dropping down. So even they're always moving like randomly, and even if they're moving over to the right, they can still move over to the left, and their direction is not related at all. And so this is for if we reduce the number of atoms, but we keep the temperature the same. If you'll go back to the graph before, we could show that around 120 atoms of the 200 moved over to the right towards the end of the 30 seconds. And then if we jump back over here, since we only have 100 atoms, it shows a pretty similar amount of, so it's around 60% of the atoms are going to go through across to the other side when it's at 300K. So we can safe to assume that around 60% of the atoms are going to move over at a certain temperature. And then if we move and we drop down, we go back up to 200 or 100 particles. And this is just the evidence for less particles, but still moving around the 30 seconds. And then if we move on to the next, this shows the graph for if we have 200 atoms, so just like we did in the first experiment, but instead of 300 Kelvin, we have 50 Kelvin. And this shows that even though we have 200 atoms, only around 25% of the atoms actually made it over to the right side. And this just shows that when temperature rises, these atoms are moving a lot quicker and quicker. So if you go to the next slide. So all of these atoms are moving around more quickly and more quickly. So if you have all of these atoms moving more quickly and they're bouncing into each other, over time, more of them are going to move over here since their velocity is higher. And because there's more of them, it'll allow more of them to go over there. But since the temperature is dropping, only a certain amount of them will be able to go across.
So the equations that we use in order to visualize this and things that we're kind of trying to prove with those models. First one is the diffusion flux equation. So D is our diffusion coefficient. dC over dx is our concentration gradient, and then J is going to be our diffusion flux. So as Ned mentioned, the diffusion gradient is proportional to the concentration gradient. That's also known as Fick's first law. So the more atoms you have on one side, the more will travel to that left side, typically. But we also have, on the next equation, we're showing that a lower temperature will also lower the diffusion. So this is what happened with that 200 atoms at 50 Kelvin, was even though it still had a high number of atoms, since the temperature was so low, the diffusion was a lot lower as well. So in this equation, we have D is our diffusion coefficient, that's what we're solving for. D0 is our initial diffusion coefficient. ED is going to be our activation energy for diffusion. KB is Boseman's constant, and then T is going to be temperature in Kelvin. So using what we modeled in this equation, it kind of proves that the lower temperature will result in lower diffusion.